So welcome to the first unit of organic chemistry. The course Chem 26 here is a mixture of organic chemistry and biochemistry. We'll look at organic chemistry first because it forms the basis of biochemistry. And it's important when we think about organic chemistry not to get too afraid. A lot of students approach this, or even before they approach it, they've already decided that they're going to fail the course, or they've heard so many awful things about organic chemistry. And I'm here to tell you that it does have a stigma associated with it, but only because it is so very different than general chemistry, the type of chemistry many of us are more familiar with. We may have had it in high school, whereas we did not have organic chemistry. So I'm going to ask you to have an open mind as we go into organic chemistry, and just keep in the back of your mind that this is just going to be very different than other types of chemistry we've looked at. This first unit is a rather large one, so we're going to be spending a number of weeks on it because we have to first introduce ourselves to the entirety of what organic chemistry is, and that's going to take a while. Also, in this unit, we're going to be looking at a particular type of functional group, a subset of organic chemistry known as the alkanes, or it's a type of functional group. We're going to learn about what functional groups are. Alkanes, the saturated hydrocarbons, but that comes at the end. That comes at the end when we look specifically at a type of organic structure. We're going to spend most of the time here, or at least the beginning part of the time, with just that introduction to organic chemistry. And if you had to sort of package up the concept of organic chemistry very nicely, you could call it the chemistry of carbon, because carbon is the basis of organic chemistry, the element carbon. Or if you wanted to be a little more sort of flowing about it, you could call it the chemistry of life, because all life as we know it is based upon the element carbon. Carbon atoms form the basis of life. When we talk about organic chemistry, when we refer to organic chemistry, there are a number of different ways in which it departs from the way we learned general chemistry, which adds to its mystique and, unfortunately, to its stigma. Whereas in general chemistry, we worked with a lot of elements, atoms of a lot of elements, metals, nonmetals. The entire periodic table was sort of up for grabs when we were working with general chemistry. But with organic chemistry, we really boil this down to only four major building blocks, four atoms, which go into almost the entirety of all organic chemical structures. There are other ones which we'll be looking at, but by far the vast majority of organic compounds are first based on the element carbon, but also on hydrogen and nitrogen and oxygen. Those four elements, I sometimes refer to them as Lego blocks, go together to make virtually an infinite number of organic molecules. And I refer to those four elements as Lego blocks because in the old days, when you bought a Lego kit, there was only like four types of blocks. There was the square one, there was the rectangular one, there was the really rectangular one, and so on. There was only 4 or 5 different types of building blocks. But from those 4 types of building blocks, if I had enough of them, I could build any number of a myriad of block towers or other things, really limited only by my imagination. And that analogy fits for organic chemistry. Very few types of building blocks, hydrogen, carbon, nitrogen, and oxygen, but an unlimited number of compounds that we can create using just those 4 building blocks. Now, importantly, and this should be derived a little bit from general chemistry, these 4 building blocks here have a predictable bonding structure. It's called the standard bonding model. And as we said before, the carbon is the basis for organic chemistry, the element carbon. And when we look at carbon, that we see a Lewis structure of a carbon atom there showing 4 valence electrons, all unpaired. And the standard bonding model stated that within these non-metals we're using, the number of unpaired electrons on the actual atom, here we have 4 unpaired electrons in this Lewis structure, tells us the number of covalent bonds which will be emanating from it in a standard bonding situation. So here we have carbon with 4 covalent bonds emanating from it. In organic chemistry, we deal exclusively with covalent bonds because the elements that go into forming organic compounds are all nonmetals, and they bond with other nonmetals, and by definition, that has to be a covalent bond. So down here, we see 4 covalent bonds emanating from this carbon atom, and they terminate in little squiggles, which means they can be attached, say, to other carbon atoms or other hydrogens, nitrogens, and oxygens, and so on. So the standard bonding model states that carbon in the standard bonding situation has 4 covalent bonds emanating from it. If we look at something else, such as hydrogen here, here's hydrogen, and it has one electron, an unpaired electron, in its Lewis structure, and thus hydrogen will have only 1 covalent bond possible emanating from it, and that's it. So this fits that standard bonding model. When we start looking at the other types of atoms, for instance, nitrogen has 5 valence electrons, but if you'll notice that 2 of them happen to be tied up as a lone electron pair, and that lone electron pair almost always does nothing. It just sits on nitrogen, even when we're in a bonding situation. But also, if you'll notice on here, nitrogen has 3 unpaired electrons. That means that nitrogen in the standard bonding model, in a standard bonding situation, will have 3 covalent bonds emanating from it because of those 3 unpaired electrons on its Lewis structure. And look at this, we have that lone electron pair that gets carried through. Always on a nitrogen in an organic structure, there is that lone electron pair, always sitting on nitrogen. And although we won't always have to show it in a Lewis structure or a bonding structure or something like that, it is implied to always be there. So lastly, now if we look at oxygen, oxygen has 6 valence electrons, and the way they are arranged is that 2 of them are in lone electron pairs, so they're just going to sit on that atom no matter what bonding situation that it's in. And we also have 2 unpaired electrons. That tells us now that oxygen in a bonding situation will have 2 covalent bonds emanating from it. And we can see that right here in this general example. That oxygen atom has 2 covalent bonds emanating from it and 2 lone electron pairs just sitting on it doing nothing. Those are always there, whether they are shown or not. Now, if you forget everything else, remember this one thing. This is essentially the standard bonding model right here. What do we have around a hydrogen? Well, we have 1 covalent bond. Look at what right here in the parentheses. Carbon always has 4 covalent bonds, no lone electron pairs. Nitrogen emanating from it has 3 covalent bonds, 1 lone electron pair. And oxygen has 2 covalent bonds and 2 lone electron pairs on it always. As long as we adhere to the standard bonding model, we can, meaning the same, having the same number, the appropriate number of bonds emanating from each of these atoms, the proper number of lone pairs on them. If we adhere to that, we have the potential to build an unlimited number of organic structures just using these 4 building blocks. So why is it that the potential number of organic carbon-containing compounds that we could build using these 4 building blocks is nearly limitless. And it can be distilled down into 3 reasons. The first one is that carbon is the only element which can form stable covalent bonds with other carbons, with other atoms of itself. And here I've got sort of a chain of carbon atoms. This is very colloquial right here, and we're going to be learning a more specific way of putting this together. But there's 5 carbon atoms put together. Notice on each carbon atom we have 4 bonds emanating from it. I don't know where all those bonds go, but that's not the point here. The point is that we see that carbon is virtually the only element that can form stable covalent bonds with other atoms of itself in a long extended structure. There are some elements that can form covalent bonds with other atoms of itself in more limited, smaller structures, but carbon can continue to do it. So if we think one reason why the number of organic carbon-containing compounds is nearly limitless is that if we look at this 5-carbon chain right here, I could, and I'd say, okay, well, what else could I make? Well, why don't I just tack on another carbon atom or tack on another carbon atom and so on and so forth. So as long as I have the ability to just tack on one more carbon atom, I have an infinite number of possible structures available to me already, without even going into the other 2 reasons why we can have much more diversity of structure, adding to the number of carbon-containing compounds being virtually limitless. So let's go on to the second reason that the number of organic carbon-containing compounds is nearly limitless. And that is the fact that carbon can form stable covalent bonds with other elements, not just other atoms of itself, as we saw above, but those 3 other building blocks. And there's a couple more that happen more rarely, but those 3 others, hydrogen, oxygen, and nitrogen that we saw before. So those are the big 4. Not only can carbon form these stable covalent bonds between other atoms of itself, it can also form stable covalent bonds with other hydrogen atoms, nitrogen atoms, oxygen atoms, and so on. Now, remember with carbon, it had to have 4 covalent bonds emanating from it all the time. That was part of the standard bonding model. And since carbon is the basis, the underlying basis of organic chemistry, it has a special sort of a heightened importance assigned to it. So because it has 4 bonds always that must be emanating from it, we call that the rule of 4. In organic chemistry, the rule of 4. Notice, anytime we see a carbon atom, it better have 4 bonds emanating from it. And since it's the most important one, when you hear the term, what is the rule of 4, it means that 4 bonds must always be emanating from carbon in an organic chemistry situation. But how those 4 bonds are put together, we don't always have to have them as single covalent bonds. Notice here we have this very crude example. They're all single covalent bonds between these carbon atoms. Well, if we look at this third example down here, why the number of organic carbon containing compounds is nearly limitless, is that carbon can form double and triple covalent bonds with itself and certain other elements, as long as the number of covalent bonds emanating from those carbons, that number remains 4. So here we have an example of a carbon-carbon double bond, a carbon-carbon triple bond. All of these we'll be looking at in much more detail in the units to come. But if you look at each carbon atom on these very crude representations, all of them, if you count, have 4 covalent bonds emanating from them. So the rule of 4 is satisfied. So let's try to tie this all together, bringing the standard bonding model into real-life molecules. As I said before, we really have very few rules when putting together these 4 building blocks. And those rules would be, for instance, oxygen must only have 2 covalent bonds emanating from it in 2 lone pairs. carbon, 4 covalent bonds emanating from it, no lone pairs, and so on. So if we follow these relatively few rules, we can put together a myriad of potential organic molecules. We just have to follow the rules of the standard bonding model. So I've got a series of molecules here. Some of them may look pretty weird. All of them probably look pretty weird to you, but this is only to show you, and we'll be building these more as we move along. But what I'd like to do with this slide is for us to inspect each molecule to see that each atom within it adheres to the standard bonding model. And if it does, then we can say, for all atoms, we can say that this is a viable organic molecule. And if it can exist, it probably does exist, at least somewhere in the universe. So if we look at the structure over here on the left, we have two carbons within it. There's 4 bonds emanating from each of those carbons. Notice 2 of the bonds are tied up in a double bond, but that's okay. There's 4 bonds emanating from each carbon and no lone pairs on the carbon, so that's fine. Each hydrogen we see has 1 covalent bond emanating from it, no lone electron pairs, so that's good too. If we look at the next structure over here, well, it's the same sort of thing. It says each carbon has 4 covalent bonds emanating from it. That carbon I highlighted right there. 3 of those 4 bonds are tied up in a carbon-carbon triple bond, but that's okay. That's one of the 3 reasons that the number of organic carbon-containing compounds are limitless, is we can have double and triple bonds between 2 carbons, or we'll find between a carbon and another element, such as oxygen or nitrogen, as long as the standard bonding model is adhered to. If we look at this next structure over here, that carbon, yes, indeed, total of 4 covalent bonds emanating from it. Each of the hydrogens, 1 covalent bond emanating from it. Now look at oxygen over here. Oxygen, if we count the number of bonds emanating from it, there's 2 of them. 2 of them. They happen to be both of them tied up in a multiple bond, but that's okay. There's still 2 covalent bonds emanating from it, and we have 2 lone electron pairs sitting on oxygen. That's part of the standard bonding model as well. Looking next door, we have this really strange looking compound in which we find that the carbon has 4 covalent bonds emanating from it. All of the hydrogens have 1 covalent bond emanating from it, and our nitrogen. That's sort of the weird one right here, but let's analyze. How many covalent bonds are emanating from that nitrogen atom? There's 3 of them, 2 of which are tied up in a multiple bond, but that's okay. That's the standard bonding model. Nitrogen has 3 covalent bonds emanating from it, always. And look at that, 1 lone pair sitting on nitrogen. That's also part of the standard bonding model for nitrogen. Lastly, over here on the far right, we have, again, some multiple bonds there, but if we count, the carbon has 4 bonds emanating from it, hydrogen only 1. This nitrogen, again, is a different sort of story from the one next to it, but again, doesn't matter. I count 3 covalent bonds, all tied into 1 multiple bond, but that's okay. 3 covalent bonds emanating from it, and I see 1 lone electron pair sitting on it. So all of these structures, well, we're just getting started here, so they may seem really foreign to you. They are all viable organic compounds, and I can tell you with certainty that all of them do indeed exist. So if we tried building something larger, and don't worry about this, these larger molecules frequently in the beginning part of the course are just templates to illustrate something. So don't get scared. So if we built a larger molecule, this is an organic molecule, it's made of carbon, hydrogen, nitrogen, and oxygen, and a couple other things thrown in there, which we will introduce momentarily, but they all adhere to the standard bonding model. Now, I will bring your attention to the fact that we have a couple different atoms here, this fluorine atom and this chlorine atom right here. And I didn't cover those in the standard bonding model on a previous slide because we were specifically looking at the 4 main building blocks of organic molecules: carbon, hydrogen, nitrogen, and oxygen. And I had said before, it's like, sometimes we get a couple outliers, different elements other than those 4 big ones in there. And this is one of the cases where we do see that. Any halogens. Halogens are the the column of elements second to the furthest on the right on the periodic table, fluorine, chlorine, bromine, iodine, and so on. Those are all halogens. And since they exist in the same vertical column of the periodic table, through periodicity, we know that they have similar reactivity. But what that really means, if you remember your general chemistry, is that all of these halogen atoms have identical Lewis structure. And that identical Lewis structure gives them similar or identical adherence to the standard bonding model. If we look over at these two atoms, halogens in the standard bonding model always have one covalent bond emanating from them and 3 lone electron pairs sitting on them. We see that in both of these cases on fluorine and chlorine. That is indeed the case. That will always be the case for any halogen, whether it be if it's attached to a covalent, an organic structure. It will always have only one bond emanating from it, 3 lone electron pairs sitting on it. We see that with the fluorine and the chlorine in this gigantic molecule right here. But again, I say don't be afraid, because this gigantic molecule that I put in front of you is only for analysis, for adherence to the standard bonding model. We'll go through this atom by atom, and if all of the atoms check out, then this is a viable organic structure, and it probably exists somewhere in the universe, very likely closer to home, somewhere on this planet, or from a chemical company, or what have you. So let's look at this. We had already decided that the two halogens, fluorine and chlorine, one covalent bond emanating from them, 3 lone pairs, were okay. Well, what about this carbon right here? That has 4 bonds emanating from it. That's okay. The 2 hydrogens connected to it are okay, because they only have 1 covalent bond emanating from it. Let's go, we'll go through this sort of on a line. What about this oxygen atom? Is that okay? Well, oxygen, if we'll remember, is supposed to have 2 covalent bonds emanating from it and 2 lone pairs. That is indeed what it has. So onward we go. This carbon, 4 bonds, no lone pairs. Check. As check out the 2 hydrogens attached to it. How about this nitrogen? Nitrogen has to have 3 covalent bonds emanating from it, 1 lone pair. That is indeed what is going on. So that's okay. Hydrogen here checks out, 1 bond. This carbon, 4 covalent bonds. That's okay. No lone pairs. The hydrogen connected to it. That's okay. This carbon, 4 bonds. Check. This hydrogen, check. This carbon, 4 bonds. No lone pairs. This oxygen, well, look at it. It's got 2 covalent bonds, 2 lone pairs. So every single atom on this molecule checks out via the standard bonding model. So we can say that it is a viable organic structure. But what if I purposely threw in some issues with a molecule? We still have to go through that molecule atom by atom to see if all of the atoms within it adhere to the standard bonding model. If only one atom does not adhere to the standard bonding model in a giant molecule like this, well, the whole molecule is defunct, and it is not a viable organic molecule. Let's look at something. Here's another scary molecule, and we can look at this atom by atom, and immediately we get some issues showing up. What about this oxygen right here? This oxygen has 3 covalent bonds emanating from it, 1 lone electron pair. That is not viable. Oxygen has to have 2 covalent bonds, 1 and 2 lone pairs. This does not. So what we're doing here is we're going through this molecule and picking out all of the atoms which don't adhere to the standard bonding model. And right next door, we'd pick out this carbon atom right here. What's wrong with that carbon atom? Well, that carbon atom has 3 covalent bonds emanating from it. So carbon, as we know, the rule of 4, has to have 4 covalent bonds emanating from it, so that is a problem as well. Notice, in this example, I'm only picking out the atoms which do not adhere to the standard bonding model. If I'm not highlighting an atom or looking at it, that means that they do adhere to the standard bonding model. Look at this carbon. That's a problem. we have 5 bonds emanating from that carbon. That's not 4, that has 1 more. In organic chemistry parlance, this is known as a Texas carbon. A Texas carbon. It's just sort of an abbreviation. A Texas carbon. Well, because everything's bigger in Texas, right? Well, apologies to anybody watching this that's from Texas, but everything's bigger in Texas. So a Texas carbon would be one with more than 4 covalent bonds emanating from it. That is not a scientific term, by the way. That's just a colloquial term. But in any event, we have a problem. Notice I'm not going to be highlighting this nitrogen down here, even though that sort of looks weird too, even though that's participating with that carbon that does not adhere to the standard bonding model. But that nitrogen does adhere to the standard bonding model. It has 3 covalent bonds emanating from it, 1 lone electron pair. That's standard. All right, let's look at another problem area on this molecule. Right there. That chlorine is a halogen. Remember from the previous one, I had said that those Johnny-come-lately halogens, their standard bonding model for them was 1 covalent bond emanating from it, which is what we see, but 3 lone electron pairs sitting on it. In this case, we have 2 lone electron pairs sitting on it, so that is a problem as well. Lastly, I'm picking out that hydrogen atom as a problem. Because hydrogen, as we know, if you look at all the other hydrogens on this entire page, it only ever has 1 covalent bond emanating from it. This one has 2 covalent bonds emanating from it, so that is a problem. So the game we just played was really, as we go through this molecule, which ones do not adhere to the standard bonding model, and which do. So we're able to move through that sort of slowly and methodically and analyze this. If even one of those atoms, we found 5, but if even one of them did not adhere to the standard bonding model, we could throw up our hands and say this whole molecule is not a viable organic structure. So in the previous slide, we had looked at the diversity of organic structures that we could build based on all 4 of those building blocks: carbon, hydrogen, nitrogen, and oxygen. But we're going to look at a specific subset of the chemistry of organic carbon here, types of organic compounds, using only 2 of those 4 building blocks, only carbon and hydrogen. And when a compound is composed solely of carbon and hydrogen, nothing else, it is considered a hydrocarbon. Hydro for hydrogen, carbon for carbon. Hydrocarbons are compounds which are only comprised of carbon and hydrogen atoms. In this case, what we see here are 2 representative examples of the literally infinite number of hydrocarbons that I could draw. And again, if we look at each of these, and now that we're only down to these 2 particular building blocks, carbon and hydrogen, we can analyze all of them to make sure that they adhere to the standard bonding model. If you look through all of these, all of the hydrogens in both gigantic molecules only have 1 covalent bond emanating from them, no lone pairs, all of those hydrogens are fine. Going through all of the carbon atoms, we have to be a little more careful here, especially with the compound on the right. But indeed, if you go through every single carbon on both of these molecules, you would find that all carbons have 4 covalent bonds emanating from each of them. Some of those 4 bonds may be tied up in double bonds or triple bonds or whatever, but the point is that all hydrogen atoms and all carbon atoms in both of these molecules adhere to the standard bonding model. Thus, both of them are viable organic structures. So staying with this idea of hydrocarbons, compounds, organic compounds only comprised of carbon and hydrogen, I want to narrow our focus a little bit and talk about only single bonded hydrocarbons. And remember on the previous slide, I had the one molecule that all had carbons put together with using single bonds. That's what I'm talking about here. The other molecule had some carbon-carbon double bonds and carbon-carbon triple bonds in that. They're important, but we'll look at those later, and I want to now narrow our focus just to look at carbon-carbon single bonds to talk about if I have a hydrocarbon that is only comprised of carbon-carbon single bonds, there are three categories that it can fit into. Three categories: linear hydrocarbon, a branched hydrocarbon, and a cyclic hydrocarbon. Let's look at examples of each of these. The linear hydrocarbon is probably the easiest to draw because it is called a linear hydrocarbon because all of the carbon atoms are in one line. They're linear, they're not exactly a line, and I draw it in this zigzag motion for reasons that we'll be looking at down the road. But notice on this hydrocarbon here, this single bonded hydrocarbon, all of my carbon atoms have 4 bonds emanating from them, and I have highlighted or bolded in the carbon-carbon bonds. Normally you don't do that, but just to get us up and running here, that shows us the carbon skeleton, and any of the regular lines are the carbon-hydrogen bonds. It's just to sort of illustrate or accentuate the carbon-carbon bond. You can see that sort of all those carbons are covalently bonded together in a line, so therefore that would be a linear an example of a linear category of single bonded hydrocarbons. Well, what would happen if we took one of those carbons in the center of that linear hydrocarbon and put a carbon branch off of it? Something like that. So if we have our linear hydrocarbon, which we see right here on this example, that's the linear hydrocarbon, and off of one of the internal carbons on it, we're sort of putting a branch right here. It's called a branched hydrocarbon because it looks like it's branched out. So that would be, we could tell immediately the difference if those two are put in front of us. Which one is the linear hydrocarbon? Which one is the branched hydrocarbon? We would quickly be able to tell. Remember, these are only representative examples of these. I could draw many different an infinite number of linear types of hydrocarbons, single bonded hydrocarbons, an infinite number of branched ones. These are just examples. The last example here would be a cyclic hydrocarbon. A cyclic hydrocarbon is where all of the carbons in, say, the line up top are set in a loop. What if they are connected so that there's no beginning and no end? Well, that would be an example, here's one in particular, of a cyclic hydrocarbon. Notice in the bolded carbon-carbon bonds, it exists in a cycle. This is very easy to look at this and say, okay, this is definitely different. This cyclic hydrocarbon is definitely different than the branched one, is definitely different than the linear one. So we would be able to tell in all three cases which category these single bonded hydrocarbons belonged to. So as long as we are dealing with single bonded hydrocarbon structure, an example, a much more intense example is shown on the bottom here, we can now start to not name each carbon atom, but classify it. Notice in the molecule on the bottom, that's sort of a mixture. You couldn't really call it, well, it's only a cyclic hydrocarbon, even though we have a cycle in it, or it's only a branched hydrocarbon, even though there's some branchings off of what appears to be a normal linear unit. It's sort of a hodgepodge, a mixture of all of them. So I would never give you something like this and say, okay, which is this? Is this a linear? Is it a branched? Is it a cyclic? I would never do that. This is just an example to qualify as classifying carbon types. As long as it's a carbon-carbon single bonded system, we can classify these. Organic single bonded carbon atoms in this molecular framework can be classified based upon the number of other carbons they are, and this is important, directly attached to, right next door. There are 4 types of classifications of carbon types: primary, secondary, tertiary, or quaternary. Notice that they can be abbreviated. Primary is given as a 1 with a little degree sign, secondary as a 2 with a little degree sign, tertiary 3 degree sign, quaternary 4 with a little degree sign. That's the abbreviation of it. You can write out tertiary, or you can write 3 with a little degree sign. It does not matter. I'm just showing you, giving you ways in which you can analyze and denote particular carbons of this, on how to classify them. We can have an infinite number of carbons in this carbon-carbon single bonded molecule, but they only classify as one of these 4. So let's look at some of these. Let's look at this carbon right here that I'm highlighting in yellow. What would be its classification? And to answer that question, all we have to do is ask how many other carbons are directly, right next door, connected to it. And I see only one that is directly right next door connected to it. We can't continue on in the chain and so on. The rule is it has to be the carbon adjacent to it. Well, there's only one of them. And thus, this would be considered a primary carbon. As would this one over here. It has only one other carbon directly adjacent to it. This would also be a primary carbon. As would this one. So we're going through these again, atom or carbon by carbon in this case, in order to classify them. That bottom carbon that I've highlighted in yellow has only one carbon adjacent to it, directly covalently connected to it. So it too would be a primary carbon. So if we continue this, well, what about this carbon right here that I'm highlighting in yellow right now? How many carbons is it directly connected to? Well, we see that there's one over on one side and one over on the other side. 2 carbons adjacent to it. So this would be a secondary carbon. Let's see how this goes. Look at these. This carbon and this carbon right here are both connected to, directly right next door, 2 other carbons. So both of these would be secondary carbons. Secondary. Let me clean this up perhaps a little bit, and we'll look at a couple more. What about this carbon atom right here? How would we classify this? Well, we just have to ask, how many other carbons is it adjacent to, directly covalently connected to? Well, I count 1, 2, 3 right next door. So this would be an example of a tertiary carbon because it's directly connected to 3. Lastly, what about this guy right here? Well, we have this carbon right here, and it is, you have to count, this is directly connected to 1, 2, 3, 4 other carbons. So on this molecule, this would be classified as a quaternary carbon. So there's one primary, secondary, tertiary, or quaternary based upon the number of other carbon atoms it is directly connected.